Okay, now we move on to the mixed questions. So first of all, we're given a plank AE of length 6 meters and weight 100 newtons rest in a horizontal position on supports at B and D, where AB equals 1 meter and D equals 1.5 meters. So at this point here, we've already got a drawing set up. Currently, we don't know if it's a uniform or a non-uniform plank, so we can't place the weight in yet. But we do know that there are supports at B and D, so therefore we can draw in some reaction forces at B and D. So this is B, this is D. A child of weight 145 newtons, so 145 newtons goes down, and the midpoint, so it stands at C, which is the midpoint of AE. Child is modelled as a particle and the plank as a uniform rod. So if it's a uniform rod, not only do you have so he's at the midpoint here, 3 meters. From the edge, you also have the weight of the plank. So you're going to have at this point here, you're going to have 100 plus 145 plus 100 because the weight of the plank as well. So plus weight is going downwards. The child is modelled as a particle and the plank is a uniform rod. The child and plank are in equilibrium. Calculate the magnitude of the force exerted by the support on the plank at B and the magnitude of the force exerted by on the plank at D. So in this case here, this is a standard question, just with modified wording. So here we assume, again, we do the first formula, up equals down. So going upwards we have B and D, and going downwards we have 145 from the child and 100 from the plank. So B plus D is equal to 245 newtons. Then we take moments. So we take moments from either B or D, it doesn't matter. So I'm going to take moments from B. When we take moments from B, we're going to have the 245 newtons is because we're going to put them together because they're at the same spot, so we can just consider it as one force going downwards. So this is going to go clockwise around, so we've got clockwise equals clockwise, so this is the 245, and then the D is going anti-clockwise around around B. So then from here we do our formula, which is moments equals force times distance. So now we've got to work out like how far away it is, so what distance is. So we know that this is 1 meter away. So we know that our distance here, we know that the halfway point here is at 3 meters. So therefore, if it's already travelled 1 meter, the distance between B and the midpoint must be 2 meters. And the same here, so this is 1.5 meters away from the edge of the plank, so it must be 1.5 meters away from the middle of the plank, and then obviously we're measuring it from B, so from the middle of the plank to B is 2, so altogether it's going to be 3.5 meters. So here we're going to say that D, it's 3.5 D, so force times distance is equal to 245 times 2, so therefore it's D is equal to 245 times 2 divided by 3.5, and from here we just plug that into our calculator, so 245 times 2 divided by 3.5, so D is equal to 140 newtons. From here we can then plug that back into our first equation we set up, B plus D equals 245, so B plus 140 equals 245, so B is equal to 245 minus 140 is equal to 105 newtons, and that gives you so here I didn't pay attention to the question order, so the question order was A and B. It doesn't matter essentially which way you solve this, as the examiner will accept either way of solving it, unless it's looking for obviously one of the ways to do it. If you do a slightly longer way, it's completely fine. So the next point here, the child now stands at different points, so we're going to rip all this out because we can change our situation. So let's rip out our working and then let's start again. So the child now stands at a different point on the plank F. So the plank is in equilibrium and on the point of tilting about D. Calculate the distance dF. Okay, so here the child is removed. We still a uniform plank, so we still have the weight that is going downwards. So if the plank is in equilibrium and on the point of tilting about D, if we draw just a brief one of the plank here, if it's about to tilt and use this as the center of rotation, then at point B, so at our position B, at the support, the beam is about to lift off from beam B. So if it's about to lift off, we say that there is a reaction force is equal to 0 newtons because the beam is just about to lift off from it. So as we're taking this as our tilting point, it's just about to lift. So if you had your pen and you have a B and D, and if you start to rotate the pen around B, you'll notice that it will start to lift off from your other point. You're rotating it around D, so B and D. So in your right hand, if you hold the pen with D and you put B as well, if you start to lift, use one of your fingers just to push up on D, you'll notice it will lift off from B. So at the point of rotation, it's just about to lift off. If it's just about to lift off, therefore the reaction force is essentially 0 because the beam is no longer applying a force downwards at that position. So that helps us because it means that we can basically ignore B. There's no force acting at B. There is still a weight. There's also still the child. So the child is now standing at a different point at F. So we can say that the child might stand maybe here. So we're going to say that this distance here is df. Now we don't know whereabouts that could be. So again, if it's a negative answer, that's completely fine. It just means that the child is standing over here instead. But if you draw a diagram and show it, then it's making it clear to the examiner where you are drawing your what distance you're taking it from. Although it is a distance, so therefore it is just a scalar property. So you don't need to include any negative signs, but if you get negative in the question, it's completely fine. Anyway, let's crack on with the question. So here, when we're considering this, we've got the child. The child is going downwards. Again, he has a weight of 145, and then we've got the weight altogether of the beam, which is 100. And that B, there is no force acting. So again, we can take. So we're going to take. There is obviously a reaction force at D. There's still that reaction force, but here we're going to ignore that because we're going to take moments from D. So if we take moments from D, this is likely to end up with a negative answer, which is good because we can see an example of that. So we're going to take our child standing at F at this point, and therefore in this position you must be consistent with your answer, with your moment. So here we've got clockwise equals anti-clockwise. So the clockwise ones, both of them are going anti-clockwise. So there is the child, so 145, and the weight, which is 100. So they're both going anti-clockwise, but there is nothing going clockwise. So here that's not a problem. It just means that one of our distances, essentially one of our assumptions is wrong, but it's completely fine in terms of the exam. You might do this in the exam as well, so it's good practice to have confidence. So here we do our distance, so we know that D is 1.5 meters away because D is halfway between, it's 1.5 meters away from E and it's 3 meters from E to the midpoint. So it's going to be 100 times 1.5 plus 145 times our distance x, and actually I should say there's just no forces acting. So this means that's equal to 0. From here we solve, so that's going to be 150 plus 145x equals 0, and then we just rearrange. So 145x equals minus 150, and then 150 minus 150 divided by 145 is equal to 30 over 29. So x is equal to 30 minus 30 over 29 meters, which gives an answer of minus 1.03 meters. So that's completely fine. So that tells us that the distance is equal to minus 1.03 meters. Of course, if you were thinking this in terms of a physical way, then the child must stand on this side to be able to balance the beam that's rotating around anti-clockwise. So therefore, logically, it makes sense that the child should stand here, because then he would apply a clockwise motion around D. But you may not think like that in the exam, so it's important that you use your assumptions and you try and stick with your assumptions all the way through in these type of questions, because you will get the right answer. You'll just get a negative. which is fine. Okay, so the next question that we have is a uniform of AB has a length of 4 meters and a weight of 150 newtons. So that's fantastic because we can then, if it's a uniform rod, we can say already that there is a force acting downwards halfway, which is 150 newtons, and this is 2 meters from A. The rod rests in equilibrium in a horizontal position, smoothly supported at points C and D. So therefore there's an upward force C and a upward force D. And we're given the distances AC 1 meter, AD 2.5. A particle of weight W newtons is attached to a rod at point E, where AE is x meters. So I'm going to say it's going to be here. This is our force our W, and this is our distance x. The rod remains in equilibrium, and the magnitude of the reaction at C is now equal to the magnitude of the reaction at D. Show that 150 W equals 150 divided by 7 minus 4x. Okay, so from here we need to do the following, which is do our upwards equals our downwards forces because the rod is in equilibrium. So going upwards is C and D, and going downwards is 150 plus W. One key thing here, I mean, it's already a good sign because you see 150, so you always refer back to your initial equation. So here we says that C and D are equal to each other, so we're just going to say, well, C is equal to D because it tells us that they're equal magnitude. Yeah, so they're now equal magnitude to D, which is equal to R. We're going to say R, so that means that it's R plus R is equal to 150 plus W, so 2R is equal to 150 plus W. Then the next thing we're going to do is we're going to take moments. So we're going to take moments, and we can take, again, our unknown. So our unknown here is W, C and D. So for this one, we want to find what W is. But we could also find something in terms of R. So essentially in this one here, you've got two unknowns. You've got R and you've got W. So you could take this in either way. So in terms of the thought process here, you could either take moments at C, but you're still left with then two unknowns, R and W. Alternatively, you could take moments at W, but then you're left with two unknown. So then you could find what R is in terms of X and then substitute that in, because remember W is in terms of X. So in this case, I am going to take moments from W in this case. So we're going to take moments from W and we're going to see how that plays. You can take it from C and D. So if we take moments about W, we've got D that is going anti-clockwise. We've got the midpoint here that's going clockwise, and we've got C here going anti-clockwise. So in this case here, let's write that in. So moments about W, we've got anti-clockwise equals clockwise. And in this situation, we're going to say, okay, so we know, so we've got D is going clockwise, C is going clockwise, and 150 is going anti-clockwise. Now in terms of our distances, this is where it gets a little bit tricky. So we're starting from W, and we need to find the distance to D. So we know that the distance from A to W is equal to X, and we know the distance from A to D is equal to 2.5. So therefore this distance here is going to equal X minus 2.5, because you go all the way along to W, and then you already know the 2.5, so the remaining part must be the whatever X is minus off 2.5 that you've already travelled, and that's that distance between D and W. So it's going to be X minus 2.5. And then we're going to do the same for the rest of them. So to the midpoint, it's going to be X minus 2, because we know X all the way through to W, but then we've already travelled 2 meters in that case to the midpoint. And then finally, we have from C to W here, it's already travelled 1 meter away from A, it's going to be x minus 1. So now we're going to put that in. We're also going to use the fact that d equals c equals r, and now we're going to put this in. So 150 is going to be 150 x minus 2 is equal to d, which was x minus 2.5, which is r now because we've replaced d with r, plus x minus 1 r, because that's our c. But remember, c is x minus 1 distance away, d is x minus 2.5 away. And they're both being replaced by r because it tells us in the question that they're equal to each other, so therefore we just replaced it with a constant value. From here we're going to expand all our brackets, so it's going to be 150x minus 300 equals xr minus 2.5r plus xr minus r. Now, why have we done this? Well, essentially what I want to get is I want to get it in terms of r. So on the left hand side it's going to be 150x minus 300, and that's going to equal xr plus xr is 2xr minus 2.5 minus 2.5r minus r is minus 3.5r. Take out a factor of r, so it's 150x minus 300 is equal to r 2x minus 3.5. So here we're going to say that 150x minus 300 divided by 2x minus 3.5 is equal to r. Now we've done that, we can then go back to our original equation, which says that 2r is equal to 150 plus w, and we're going to replace r in here. So r is going to be 150x minus 300 divided by 2x minus 3.5 times by 2 is equal to 150 plus w. Now from here we go back to it. So our goal here is 150 over 7 minus 4x. So in this situation we're going to minus 150. So let's times this by 2 first. So that's going to be 300x minus 600 divided by 2x minus 3.5 is equal to 150 plus w, and then we're going to subtract off 150, so 300x minus 600, and then that's divided by 2x minus 3.5 minus 150 equals w. So here now we need to do some algebraic manipulation. So the first thing I would do here is so I'm going to times top and bottom by 2x because I want to get this with a denominator of 2x minus 3.5. So it's 3x minus 600 over 2x minus 3.5 minus 150 over 2x minus 3.5, and times the top by that as well, and that's equal to w. From here I'm going to put this together now, so it's 300x minus 600 minus 300x from 150 times 2x, and then we've got 150 times 3.5, so then plus 525, divide all that by 2x minus 3.5 is equal to w. From here we can see straight away that the 300x cancel, and then minus 600 plus 525 is equal to minus 75. So it's going to be minus 75 divided by 2x minus 3.5 is equal to w. Now we need to compare our answers. So what we can do is we can times top and bottom by minus 2. So in this one you can manipulate the equation. So we can times top and bottom by minus 2. If we do that, we get 150 divided by 4x minus 4x plus 7, which is equal to w. And that is how you can manipulate it, because that's the same as w equals 150 7 minus 4x. So this one is a very big algebraic slog, but it shows you that you can take your moments from anywhere and solve. The other method to do it would have been to get another equation in terms of w and r, and then solved it simultaneously using your calculators. So yeah, that's your answer for this one, but you've had to do it algebraically actually, so you couldn't use your calculator. So it's just a long slog, this one, to get your answer. So the next thing then is hence deduce the possible values of x. Okay, so first of all, we know that because the length of the rod is 4, that x must be less than 4. And then w equals 150 over 7 minus 4x. So in this situation here, we know that it's impossible for 1 over 0. So that's not possible. So cannot equal here. So that means that 7 minus 4x, what we can do is we can find the minimum value for x by solving this equation. So it's going to be 7 equals 4x, and then 7 over 4 is equal to x. Now this value is essentially going to be our minimum possible value, because if x is so this is going to be our highest possible value, not our minimum value. The reason why it's going to be our highest possible value, because w, we're told, so let me just remove some of our working. So a particle of weight is attached to w at e. So if the particle is at weight, it means that w has to act downwards. So therefore 150 over 7 minus 4x must be greater than 0. Now, what does that mean? Well, it means that here 7 minus 4x has to be greater than 0 here. So therefore, when we rearrange, it's 7 over 4, which we've already done. So 7 over 4x. So 7 over 4 is greater than x. So therefore, x is less than 7 over 4, but obviously x is going to be greater than 0. But it could also be at a. There's nothing stopping it being at a. Our situation just says that x has to be less than 7 over 4. So in this situation here, your possible values for x are 0 is less than or equal to x, which is less than 7 over 4. Note that it cannot be equal to 7 over 4 because that would give you a denominator of 0, but while it can be equal to 0 here because that will give you the weight. That will be a valid answer, and it will be a positive answer. And that is the end of your question for part B. So I'm going to remove the board here, and we're going to continue to question 3. So a uniform plank, so again, we can place this in the middle. So a uniform plank, this is in the middle, and this is going to be 40G. It's supported in a horizontal position by 2 pivots, so that means that that's going upwards at A, going upwards at C. And we're given our and also we're given that the length is 4 meters, so we know that this must be 2 meters away from either side. Where AC is 3 meters, a man of mass 80 kilograms stands on a plank which remains in equilibrium. So there's going to be a man, we can just use it as a particle. So a man stands here and he has a mass of 80, so therefore must have a weight of 80g. Remember, you've got to convert your mass to weight, so multiply it by gravity. A center of picture which remains in equilibrium. The magnitude of reaction A is twice the magnitude of C, so that means that 2C is equal to A, and the magnitude of C at C is R newtons, so we know that C is equal to R, so therefore 2C is equal to A, therefore 2R is equal to A, and the plank is modelled as a rod, and the man is modelled as a particle. Find the value of R. Okay, so to find this value here, we're going to do upwards equals downwards. That should be your first port of call in these questions. So we've got A plus C is equal to 40g from the weight, that's going downwards, plus 80g from the man. And we know that we've been told already that C is equal to R and A is equal to 2C, therefore 2R. It's going to be 2R plus R is equal to 120g. So 3R is equal to 120g. R is equal to 40g. So in terms of newtons, 40 times 9.8 is equal to 9.81, sorry, is equal to 392.4 newtons. So that tells us our R value, and then we want to find the distance of the man from A. So we want to find the distance from A of the man, so we're going to take moments. So here we could take moments from any point. Because we want to find the distance from A, I'm going to take moments from A. The reason why we can take it from any point is because we know, apart from the distance from A to the man, we know all the other values. We know C is equal to R. So we could take moments from A. So if we go through here, we've got the weight, so anti-clockwise equals clockwise. The weight is going clockwise, so that's our 40g. We've got R, which is going this way round, so that's also equal to 40g. So that's going anti-clockwise. Then we've got a man, which is at 80g. So then from here we can solve. So our anti-clockwise one is C, and that's 3 meters away. So it's 3 times 40g. Be careful with this one because you've got the reaction force from C, which is R, so that's C, and that's your weight. So just be careful which distance you use. So it's going to be 3 times 40g is equal to the weight, which is also 40g, times by 2 because it's halfway, plus the distance, which we're going to take as x, from A, and 80g. Remember, we don't know where the man is yet. Then from here we just solve. So it's 120g is equal to 80g plus x 80g. We subtract 80 from 120, which gives you 40g, equals 80gx, and then we divide through. So it's going to be 40g divided by 80g, which is equal to x. So x is equal to 1/2 meters, and that tells you your distance from the man to A, or A to the man. And the last one, state how you have used a modelling assumption. So if the plank is uniform, then the weight is in the middle of the plank, or taken as middle of the plank. It means that the weight, essentially, the weight is distributed evenly, or the mass, you could say as well, distributed evenly, should I say, across the plank, and that gives it its uniform. If it's non-uniform, that means that the plank's weight is essentially over to one side, and therefore the centre of mass cannot be in the middle. The plank is a rod. It means that it's essentially all the mass is in a straight line. That is literally it. So all the mass is spread out. It's not curving or anything like that. It's just a straight one. And then the last one, the man is a particle. That means that the man's weight acts on one spot. So it's essentially one finite spot. So obviously in reality that doesn't happen. The man has two legs, unless he's standing on one leg, but then even that acts over his foot, which is not exactly one finite position. So we just say that it acts on one spot. So essentially all his weight acts on one infinitesimally small, but he just acts on one position, and therefore we just take that distance. And with this, we don't consider any of essentially the dimensions of the man. And that is it for these questions. Any further questions, please let me know.